Earthquake engineering is an interdisciplinary branch of engineering that designs and analyzes structures, such as buildings and bridges, with earthquakes in mind. Its overall goal is to make such structures more resistant to earthquakes. An earthquake engineer aims to construct structures that will not be damaged in minor shaking and will avoid serious damage or collapse in a major earthquake. Earthquake engineering is the scientific field concerned with protecting society, the natural environment, and the man-made environment from earthquakes by limiting the seismic risk to socio-economically acceptable levels. Traditionally, it has been narrowly defined as the study of the behavior of structures and geostructures subject to seismic loading. It is considered as a subset of structural engineering, geotechnical engineering, mechanical engineering, chemical engineering, applied physics, etc. However, the tremendous costs experienced in recent earthquakes have led to an expansion of its scope to encompass disciplines from the wider field of civil engineering, mechanical engineering and from the social sciences, especially sociology, political science, economics and finance. The main objectives of earthquake engineering are: foresee the potential consequences of strong earthquakes on urban areas and civil infrastructure, design, construct and maintain structures to perform at earthquake exposure up to the expectations and in compliance with building codes. A properly engineered structure does not necessarily have to be extremely strong or expensive. It has to be properly designed to withstand the seismic effects while sustaining an acceptable level of damage. Seismic loading. Seismic loading means application of an earthquake-generated excitation on a structure. It happens at contact surfaces of a structure, either with the ground, with adjacent structures, or with gravity waves from tsunami. The loading that is expected at a given location on the Earth's surface is estimated by engineering seismology. It is related to the seismic hazard of the location. Seismic performance. Earthquake or seismic performance defines a structure's ability to sustain its main functions, such as its safety and serviceability, at and after a particular earthquake exposure. A structure is normally considered safe if it does not endanger the lives and well-being of those in or around it by partially or completely collapsing. A structure may be considered serviceable if it is able to fulfill its operational functions for which it was designed. Basic concepts of the earthquake engineering, implemented in the major building codes, assume that a building should survive a rare, very severe earthquake by sustaining significant damage but without globally collapsing. On the other hand, it should remain operational for more frequent, but less severe seismic events. Seismic performance assessment. Engineers need to know the quantified level of the actual or anticipated seismic performance associated with the direct damage to an individual building subject to a specified ground shaking. Such an assessment may be performed either experimentally or analytically. Experimental assessment. Experimental evaluations are expensive tests that are typically done by placing a model of the structure on a shake table that simulates the earth shaking and observing its behavior. Such kinds of experiments were first performed more than a century ago. Only recently has it become possible to perform one-to-one scale testing on full structures. Due to the costly nature of such tests, they tend to be used mainly for understanding the seismic behavior of structures, validating models and verifying analysis methods. Thus, once properly validated, computational models and numerical procedures tend to carry the major burden for the seismic performance assessment of structures. Analytical, numerical assessment. Seismic performance assessment or seismic structural analysis is a powerful tool of earthquake engineering which utilizes detailed modeling of the structure together with methods of structural analysis to gain a better understanding of seismic performance of building and non-building structures. The technique as a formal concept is a relatively recent development. In general, seismic structural analysis is based on the methods of structural dynamics. For decades, The most prominent instrument of seismic analysis has been the earthquake response spectrum method, which also contributed to the proposed building codes concept of today. However, such methods are good only for linear elastic systems, being largely unable to model the structural behavior when damage appears. Numerical step-by-step integration proved to be a more effective method of analysis for multi-degree of freedom structural systems with significant nonlinearity under a transient process of ground motion excitation. Basically, numerical analysis is conducted in order to evaluate the seismic performance of buildings. Performance evaluations are generally carried out by using nonlinear static pushover analysis or nonlinear time history analysis. In such analyses, it is essential to achieve accurate nonlinear modeling of structural components such as beams, columns, beam-column joints, shear walls, etc. Thus, experimental results play an important role in determining the modeling parameters of individual components, especially those that are subject to significant nonlinear deformations. The individual components are then assembled to create a full nonlinear model of the structure. Thus created models are analyzed to evaluate the performance of buildings. The capabilities of the structural analysis software are a major consideration in the above process, as they restrict the possible component models, the analysis methods available, and, most importantly, the numerical robustness. The latter becomes a major consideration for structures that venture into the nonlinear range and approach global or local collapse, as the numerical solution becomes increasingly unstable and thus difficult to reach. There are several commercially available finite element analysis softwares such as CSISAP 2000 and CSIPERFORM 3D and SIA Engineer tools, which can be used for the seismic performance evaluation of buildings. Moreover, there is research-based finite element analysis platforms such as OpenSAIS, IUAUMOKO, and the older DRAIN 2D, 3D, several of which are now open source. Research for earthquake engineering. Research for earthquake engineering means both field and analytical investigation or experimentation intended for discovery and scientific explanation of earthquake engineering-related facts, revision of conventional concepts in the light of new findings, and practical application of the developed theories. The National Science Foundation is the main United States government agency that supports fundamental research and education in all fields of earthquake engineering. In particular, it focuses on experimental, analytical and computational research on design and performance enhancement of structural systems. The Earthquake Engineering Research Institute is a leader in dissemination of earthquake engineering research-related information both in the U.S. and globally. A definitive list of earthquake engineering research-related shaken tables around the world may be found in experimental facilities for earthquake engineering simulation worldwide. The most prominent of them is now E-Defense Shake Table in Japan. Major U.S. research programs. NSF also supports the George E. Brown, Jr. Network for Earthquake Engineering Simulation. The NSF Hazard Mitigation and Structural Engineering Program supports research on new technologies for improving the behavior and response of structural systems subject to earthquake hazards, fundamental research on safety and reliability of constructed systems, innovative developments in analysis and model-based simulation of structural behavior and response, including soil structure, interaction, design concepts that improve structure, performance and flexibility, and application of new control techniques for structural systems that advances knowledge discovery and innovation for earthquakes and tsunami loss reduction of the nation's civil infrastructure and new experimental simulation techniques and instrumentation. The NEES network features 14 geographically distributed, shared-use laboratories that support several types of experimental work: geotechnical centrifuge research, shake table tests, experiments, large-scale structural testing, tsunami wave basin experiments, and field site research. Participating universities include Cornell University, Lehigh University, Oregon State University, Rensselaer Polytechnic Institute, University at Buffalo, State University of New York, University of California, Berkeley, University of California, Davis, University of California, Los Angeles, University of California, San Diego, University of California, Santa Barbara, University of Illinois, Urbana-Champaign, University of Minnesota, University of Nevada, Reno, and the University of Texas, Austin. The equipment sites in a central data repository are connected to the global earthquake engineering community via the NISHUB website. The NIS website is powered by Hub Zero software developed at Purdue University for NanoHub specifically to help the scientific community share resources and collaborate. The CyberInfrastructure, connected via Internet 2, provides interactive simulation tools, a simulation tool development area, a curated central data repository, animated presentations, user support, telepresence, mechanism for uploading and sharing resources, and statistics about users and usage patterns. This cyber-infrastructure allows researchers to securely store, organize and share data within a standardized framework in a central location, remotely observe and participate in experiments through the use of synchronized real-time data and video, collaborate with colleagues to facilitate the planning, performance, analysis, and publication of research experiments, and conduct computational and hybrid simulations that may combine the results of multiple distributed experiments and link physical experiments with computer simulations to enable the investigation of overall system performance. These resources jointly provide the means for collaboration and discovery to improve the seismic design and performance of civil and mechanical infrastructure systems. Earthquake simulation. The very first earthquake simulations were performed by statically applying some horizontal inertia forces based on scaled peak ground accelerations to a mathematical model of a building. With the further development of computational technologies, static approaches began to give way to dynamic ones. Dynamic experiments on building and non-building structures may be physical, like shape table testing, or virtual ones. In both cases, to verify a structure's expected seismic performance. Some researchers prefer to deal with so-called real-time histories, though the last cannot be real, for a hypothetical earthquake specified by either a building code or by some particular research requirements. Therefore, there is a strong incentive to engage in earthquake simulation, which is the seismic input that possesses only essential features of a real event. Sometimes earthquake simulation is understood as a recreation of local effects of a strong earth shaking. Structure simulation. Theoretical or experimental evaluation of anticipated seismic performance mostly requires a structure simulation which is based on the concept of structural likeness or similarity. Similarity is some degree of analogy or resemblance between two or more objects. The notion of similarity rests either on exact or approximate repetitions of patterns in the compared items. In general, a building model is said to have similarity with the real object if the two share geometric similarity, kinematic similarity and dynamic similarity. The most vivid and effective type of similarity is the kinematic one. Kinematic similarity exists when the paths and velocities of moving particles of a model and its prototype are similar. The ultimate level of kinematic similarity is kinematic equivalence when, in the case of earthquake engineering, time histories of each story lateral displacements of the model and its prototype would be the same.